Okay, getting into our final FRQ day here, accumulation focus. A couple of notes just to kind of keep us remembering kind of what's involved with these types of problems. So we've written down this before, both on the tabular data day as well as on the FF prime F double prime graph day. A reminder that a derivative is a rate or slope, a rise over run, right? Something like that. A reminder with these problems in particular, because these oftentimes are word problems, and so it's good to keep in mind just in case you have some sort of word problem on this year's AP test. Careful with the idea of, and I'm going to put decreasing. But again, remember, the word isn't always decreasing. Sometimes it's going down. But remember that those kind of words are negatives when you're coming to, or when it comes to derivatives or rates. So make sure you're watching for those kind of negative words. Okay? An integral, as a reminder, is something about a total, right? Like a how much, how many, some total there. Accumulation. Accumulating volume, area. With our FF prime, F double prime graphs, we talked about watching for below the x-axis on tabular data. We said watch for starting values. And so I'm actually going to put that one down again because I'd say that is more common with these word problems. So watch for starting amounts. We'll put that. I don't remember exactly what I put on the tabular data day, but something like that. So watch for starting amounts. Okay. And then again, back on that tabular data day, we talked about, so I called it, I think if I remember correctly, watch for comparison rates. And so for today, I think I'm actually going to write it as watch positive versus negative relationships. And so I think I drew something along these lines on the tabular data day, saying like if you have, for example, an A of t rate going in, this is a positive. A B of t rate coming out, that's a negative. The rate inside then would be A of t minus B of t, right? Going in minus coming out. And then talked about like if you needed an amount inside, your starting amount, if you had some starting amount, plus the total that went in, minus the total that went out, right? We wrote all that down back on the tabular data day. And then units, we talked about on tabular data day. Make sure that you will always write them no matter what. So units, make sure you write them, because sometimes those are their own point, right? Make sure you, wait, sorry about that. Make sure you write them no matter what. Don't give up that point, right? I mean, you don't know that it's going to be a point. We don't see the rubric ahead of time, but a lot of times it's a point, so make sure you're careful with units. I don't think we've written this down, but we've talked about it over different FRQs that we've done over this last time, but let's go ahead and jot it into our notes here just to remind ourselves that an integral with units takes away a time unit. Right, so if you think about position to velocity to acceleration, acceleration is like meters per hour squared. If I integrate acceleration, I get velocity, which is meters per hour, right? We've taken away a time. If I integrate velocity, which is again meters per hour, I get position, which is just meters. The hour has gone away. Versus a derivative, just as a reminder, so I'm going to call it a ddx or a ddt or whatever it is. The derivative adds time, so adds a time unit. So again, think about position, velocity, acceleration, position, its derivative is velocity. Positions units would be meters. Velocities units would be meters per hour. You added a time. If you take the derivative of velocity, you get acceleration. Velocities units are meters per hour. Accelerations units, meters per hour squared. You added a time. And so that's a good thing to kind of keep in mind. And again, we've talked about it in different FRQ videos, but I wanted to make sure that it was specifically written in one of them. Okay? Okay, so I only did 3 in this particular one. You're going to see, again, like I said, I went back and forth about whether or not to do them at all, but I think they give us a good chance to look at some important vocabulary. So you're going to see 2 others this week. Again, more, like I said, more to look at the vocabulary side of things, as well as, honestly, to give us a chance to kind of look at some slightly more challenging ones. Accumulation problems a lot of times are ones that I have found students tend to struggle with more. And again, you might not, but I find they're ones that students tend to struggle with more. And so in a way, it's a nice thing that you won't have to worry overly much about the calculator side of things. But it's important that we look at some challenging problems, because the reality of this year's AP test is you need to, again, expect to see some hard concepts, some hard ideas. You won't be able to answer every problem. That's just not or at least you need to expect not being able to answer every problem, but give every problem a shot. Every part of the problem, if you hit a part B that's challenging, we'll skip part B, move on to part C, right? All those testing strategies we've been talking about, they're at play. And so the accumulation problems are going to be a good chance for you to practice that. Not letting a hard part of the problem throwing you, starting to look at strategies you could use to maybe grab some points. And so that's how I'm kind of viewing these accumulation problems. This is a chance for us to navigate those testing strategies. As well as, like I said, reviewing some vocab, some concepts that could be on the AP test this year, even if they won't look exactly like these problems. They could look similar, right? But they'd have to be non-calculator, not calculator, right? Okay, so here we go. Grass clippings are placed in a bin where they decompose. For 0 to 30 for your time, the amount of grass clippings remaining in the bin is modeled by that function, where A of t is measured in pounds and t is measured in days. Okay, so we're doing 3. My recommendation, watch 1, maybe 2, but either at the end of the first one or at the end of the second one, try 1 or 2 of them on your own. Again, just so you're kind of getting some practice in navigating the strategies, navigating the vocabulary on your own. Okay, so here we go. As I look at accumulation problems, I'm always looking for a couple of key components. A lot of times your accumulation problems have what we talked about on our notes, which is these types of relationships, some rate that's going into something or onto something, right? Increasing something that's decreasing it, and then potentially some sort of starting amount. So when I look at accumulation problems, I'm looking for these things. And I want to be clear, this idea could potentially be on the AP test this year, right? It's why we already talked about this idea back with tabular data. Okay, so this is a good thing to be reviewing right now. Right? Even though we won't see a problem exactly like this one this year, because again, this is a calculator one, right? But this idea of looking for those relationships is a good thing to keep in mind, right? And so as I'm looking at this, I look at my 2014, grass clippings are placed in a bin where they decompose, the amount of grass clippings remaining in the bin. So they've actually already given me the in the bin value here, as opposed to something going into and coming out of, but that's in the bin. And that function is measured in pounds, so I've got some units here to keep in mind, days, and then always make sure you take care of, or take note of those boundaries, right? Boundaries, again, could be something that you would need to consider within the problems you see this year on the AP test. So take a look at those, right? Okay, A, find the average rate of change of A of t over the interval 0 to 30. Okay, average rate of change could show up this year on the AP test, right? So this is a good thing to remind ourselves of how to do. This comes out of 4.4, okay? average is 1 over b minus a times the integral from a to b. So that's average, right? There's my a and my b. And then average what? It's average rate of change of a. Well, what is a rate again? Rate is, remember, a derivative. So this is average derivative of a. Okay? And so then if we integrate that derivative, we get just a. Because integrals and derivatives cancel. Plugging in the upper, we have a of 30 minus, plugging in the lower, a of 0. Oops, I already plugged in, so I don't have that anymore. Sorry, plugging in the upper minus plugging in the lower. And then again, we'd use our calculator on this one. For this particular year especially, like I said, you would not be expected to be able to evaluate this by hand. That being said, another kind of quick reminder for this year's AP test, as you heard me say several times, and you'll hear me say it a couple more times this week, you don't have to simplify anything. So if on this year's AP test you get some function, maybe, I mean, again, it would surprise me if it was this function in particular, but if you got some function on the AP test that you, for some reason, were not comfortable evaluating, well, then don't. Plug in and call it good, right? So if I wanted to, looking at this function, I'm going, I don't know how to plug in 30 to that. Well, don't. 6.687, 0.931 to the 30th minus 6.687, 0.931 to the 0. Right? And call it good. You've got your answer. Right? Obviously, if you used your calculator in this particular case, you would get negative 0.197 or negative 0.196, depending on if you truncate or if you round. Okay? Okay. Oh, by the way, this one was worth 1 point. Let me pull out a pen here so I can continue to notate those things. Okay? 1 point for the answer. Okay? Final thing here, to earn that point, the other thing we do have to do is make sure that we indicate our units of measure. If we had left that off, we would then lose that point. And so we've just found the average rate of change. So we had a prime plugged in here, which was so A of t would be pounds. And so A prime would be pounds per day, right? So adding a time in every time you take the derivative, be pounds per day, right? Or you could look at it this way. These values here come from A of t. They are pounds, and we've divided by the time element, days here, so pounds per day. Maybe you prefer to get it that way, whichever way is kind of more comfortable for you, or there are other ways to think of it. So if neither of those work for you, send me an email. I'm more than happy to construct a little mini video or have a conversation with you or whatever you need to help you navigate that if you'd like. Okay? Okay, B, find the value of A prime of 15, and then using correct units, interpret the meaning of the value in the context of the problem. Again, this could be something that shows up this year on the AP test, asked to find a derivative, being able to explain what that derivative means, right? And so it's a good thing to review, even though it won't, again, look exactly like this problem, because again, this problem's a calculated problem, okay? I'm gonna stop saying that. Here we go, find the value of A prime of 15. So obviously this year's AP test, you potentially might need to actually take the derivative by hand, although again, it would surprise me if it was this function in particular. For the record, for those who are wanting to take this derivative by hand, this is an a to the u rule. So it'd be, right, a to the u times u prime times the natural log of a. And so if you were wanting to take this derivative by hand, this is a coefficient, you'd leave it alone, and then do a to the u times u prime times the natural log of a, and then plug your 15 in and leave it alone, okay? If you wanted to use your calculator, you could use your derivative button, and again, we've demonstrated that in the past, so if you need another video walking you through how to do a derivative in your calculator, let me know. More than happy to create a little calculator video for you if you would like. I'm definitely still here to support you, but maybe use your calculator for this one to calculate that derivative, and you should get negative 0.164. Which I rounded. If you which I rounded. If you truncated, you'd get negative 0.163. Okay? That, for the record, was its own point. And then second point is being able to describe what that means. So what is A prime? Well, A, remember, is the amount of grass clippings remaining in the bin. A prime, then, is the derivative of that. Well, we can't just say derivative, right? So what's another word we could use besides derivative? Okay, remember, a derivative is a rate, right? And so this is the rate at which the amount of grass clippings in the bin is, and then you're going to want to be careful here, right? So this is the rate, the amount of grass clippings in the bin, right? We just said A prime, derivative of A is what we just said. If you're going to say decreasing, make sure you're careful. This was negative already, and so if you're going to say decreasing, make sure you remove that negative. If you're going to say something that doesn't imply a negative, changing, then you would leave the negative there, right? All that stuff we talked about in related rates. I'm going to say decreasing. The rate at which the amount of grass clippings in the bin is decreasing is 0.164. And then it would be pounds per day, right? A of t was pounds, so A prime adding a time, right? Every time you take the derivative, it adds a time unit. So it'd be pounds per day for A prime. Okay? And this would be at day 15. Okay? I'll go ahead and make sure that the rubrics for these questions are also attached. College Board had a slightly different way of saying it. Maybe you like their flow a little bit better. Just so you can see another way of writing this. Okay? Okay. 3C. Find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the time interval 0 to 30, okay? So we're going to find t for which the amount of grass clippings, so we're doing, that would be our A of t, that's what the amount of grass clippings is, right? The amount of grass clippings is modeled by A of t. So where is the amount of grass clippings in the bin equal to the average, so 1 over b minus a times the integral from a to b, so average, and then average what? Amount of grass clippings. So what's going inside of our integral? Well, amount of grass clippings in the bin is A of t. And potentially speaking, solving equations could be something that shows up. Again, it wouldn't be for this one. Would surprise me exceedingly if they asked you to integrate this function. I'm pretty sure they wouldn't, right? So you wouldn't, it probably wouldn't be this one. But being able to solve an equation or set up an equation could be something that shows up on the AP test. And so just going kind of piece by piece through the problem, right? Find the time t for which the amount of grass clippings in the bin, okay, how do I write that? A of t equal to average amount of grass clippings, and so just piece by piece working your way through the sentence, setting up what they're asking you to solve for, and then being able to solve. Obviously with non-calculator ones, you're going to be looking potentially to get it equal to 0, so you could maybe factor or do quadratic formula if you don't like factoring for some reason. Potentially being able to integrate, again, probably would be a different function, right? So that would probably be more how it would look on this year's AP test. Obviously, for this particular problem back in 2014, they then used their calculator. And so go ahead and take a moment, refresh how to plug an integral into your calculator. If you don't remember, send me an email. I'll make a video of that. But if you plug that into your calculator, you should get, let me go ahead and set that up here. 30 times math 9, 0 to 30 of our 6.687 times our 0.931, 0.931 raised to the x power, and you should get this 2.752635, right? And then subtracting that over to the other side. Obviously, we are not going to be factoring like you would this year. Again, during 2014, they then plugged this into their y equals and calced their 0. This year, you would be looking, like I said, to do some sort of factoring or something like that, potentially using your 0, though, because you can use your calculator to help you out, and so maybe you want to plug it into your calculator. Could help you get out of a tough situation, help you check your work, that kind of thing. So it's a good thing to remember how to calc a 0, and so go ahead and take a moment, plug this into your calculator, calc that 0. I don't remember if I've shown this on a video yet, so I am going to go ahead and review calculating a 0. If you want to fast forward the video, go ahead and do so. 2.752635108. Okay, and so calculating 0, you'd be looking here where it touches the x-axis. You do second calc, F5, analyze graph, kind of whatever calculator you have. You do 0, which is here number 2, and each calculator will ask you a different set of questions. For 83s and 84s, they do left bound, right bound, that kind of thing. 89s, I believe, do lower and upper, which is essentially the same thing, left and right. And so you can either scroll or you can type in. So I scrolled for that one. Let me go ahead and type in for this one. 83s and 84s will ask you for a guess, and it'll give you 12.414. Right? Okay, and so then this particular year, 2014, they got 1 point for doing just the integral piece, the average piece, and 1 point for their answer. Okay. And then this last part was worth 4 points. Okay, so linear approximations, again, could show up. We've done quite a few of these over the last several weeks, so here's another one. We have for t greater than 0, the linear approximation at t equals 3 is a better model. Use that linear approximation to predict the time at which there will be 0.5 pounds of grass clippings remaining in the bin. Okay, so let's go ahead and do our tangent line approximation here. Remember, anytime you see that set of instructions, find the equation of the tangent line, right? Something about an equation of the tangent line, you should be thinking y minus y1 equals m times x minus x1. Okay, in this particular case, we're finding it at t equals 30. Which I don't want to use L of t and t, so I'm going to go ahead and change those to x and y. I prefer using x and y. You can use L of t and t if you'd like. Okay, so t equals 30 is our x1. Okay, so what's our y1? Well, our y1 is when we take that x and we plug it into our equation. So you'd use your calculator, you'd plug in your 30 into that equation, which again, surprised me if it showed up that way this year. But plugging our 30 in here, we should get negative 1.969707. Oops, sorry, I had to write a little small there. Oops, nope. That is not the right equation. I'm sorry. I'm using the equation with the minus 2.752. Actually, let me just rewrite this equation. I'll give a little bit more room for my y1. Okay. 0.782 9279. And then your derivative, so second calc derivative would be negative 0.055976. Okay? And so that would be your tangent line. Then use that to find out at what time t, so we're going to be solving for our x here, would we have 0.5 pounds of grass left over. So I'm plugging that 0.5 in here. Okay. And then dividing this underneath, we have 0.5 minus 0.782, 9279. And then we'd be left then with the x minus 30, adding the 30 over, we'd get our value of x. Okay? And then if you were to plug that into your calculator, it would give you 35.054, approximately speaking. Okay, like I said, this year was worth 4 possible points. Those 4 points, 2 were for the tangent line approximation. 1 was just for knowing that 0.5 should be plugged into L of t, not into t. And so again, talking testing strategies, even if you have something where you're like, ugh, like I'm not super comfortable, like I don't know exactly what I'm supposed to do. I don't know how to set up part of my equation, but I know how to set up this part. But put down anything you can think of related to the problem, even if it's just making some equation for L of t, but knowing to plug 0.5 into your L of t, because they've told us that we're trying to find 0.5 pounds of grass clippings, and so you know that that's L of t and not t. So you're putting, literally, like I said, putting anything down you can think of related to the problem, because you got 1 point just for knowing that 0.5 should get plugged into L of t and not into t in your equation, right? So don't leave anything blank. Anything you can think of related to the problem, put it down if you get stuck. And then 1 point came from your answer. Okay? Okay, so again, we're going to do 2 more here. You can maybe watch 1 more or pause it now and then try the next 2 on your own, or at least pause and try 1 on your own. We're going to do the 2015 one next. Again, keep in mind that focus, which is we're focused more on reviewing the vocab side of things. We're focused on practicing some of our testing strategies, which is on the parts that are a little bit more challenging, doing something, right? Putting anything you can think of related to the problem. Because again, the reality of this year's AP test is you need to make sure you're prepared for the fact that there will be parts of the problem that are going to be hard. It's how College Board structures these problems. You need to be prepared for maybe not finishing everything, right? But putting something down for each problem, giving it your best shot, right? Okay, here we go. 2015 here. We are looking at the rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is that, cubic feet per hour, t is measured in hours, and t is between 0 and 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by that, cubic feet per hour, where again t is between 0 and 8. There are 30 cubic feet of water in the pipe at time t equals 0. And so like I said at the beginning of 2014, I myself, when I look at these types of problems, I'm looking specifically for these kinds of relationships here. It's actually handy that I drew this one as a pipe because we are talking about a drain pipe here. So I'm actually going to draw a very similar picture. Okay, and flowing into our pipe, we've got our R of T. Flowing out of our pipe, right, allowing water to drain out the other end, is D of T. That means inside of my pipe is R of T minus D of T. And if they do end up needing me to find some sort of total, I'm going to look for my starting amount, which I think they gave me one. Yes, they did. There already are 30 cubic feet inside the pipe, so we have our 30, which would be plus the integral or total. Remember, that's what an integral is. It's a total. Total of R of T minus the total of D of T. We started with 30. This amount went in. This amount went out. Okay, so this is the derivative of the pipe. This is the amount in the pipe. And we've got a bunch of units here. Cubic feet per hour for D of T. Same for R of T. Okay. A, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? So what's the total that went into the pipe? So total, again, is an integral. And we're just talking in this case about flowing into the pipe. So the total what? What's the into the pipe? Well, the total into the pipe is R of T. And then you would use your calculator, okay, for this one to get 76.570. This one was worth 2 points. One for the integrand, one for the answer. Okay? B, is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for your answer. This is another thing that very easily could show up on this year's AP test, which is knowing what makes something increase or decrease. We reviewed this several times. For example, on your FF prime, F double prime graph day, we talked about what does it mean for something to increase? What does it mean for something to decrease? Okay. Well, increase means positive derivative. Decrease means negative derivative. Okay, and we're talking about in the pipe. So what's the derivative of in the pipe again? In the pipe, that's the R of T minus D of T. Right, and so the question is that R of T minus D of T at T equals 3 positive or negative? So then you pick up your calculator, plug in 3 to R minus plug in 3 to D, calculate that, and you should get negative 0.313632, which what does that mean? Well, that means we are decreasing. We have a negative derivative. So you'd say decreasing because R of 3 minus D of 3 is less than 0. Okay? Or something like that. Again, remember there are other ways you could potentially explain it. If you thought of it a different way, feel free to check it with me. I'm more than happy to say yes, you're good to go, or not. This one was worth 2 points. 1 point was for your answer with reason. And 1 point was for considers R of 3 and D of 3, which supports, again, we're talking testing strategies here, supports a testing strategy that I shared a couple of times over different videos. If you don't know what to do something, right? Define stuff that you're reading in the problem, put anything down you can think of, but then do something. Do a derivative if you think it kind of sounds like maybe a derivative. Do an integral if you think like, well, it kind of sounds like an integral. Or if you really are out and out stuck, go, well, I've got a 3 and I've got some equations. And so I'm going to plug 3 into my equations and I'm going to write that down. Because you never know, you might grab a point from that. Okay? So do something. Don't leave it blank. Never leave a part of a problem blank. You still might get no points, right? But you definitely will get no points if you leave it blank. So don't leave it blank. Put anything down you can think of that might pertain to that part. Okay? Okay, C, we have at what time t between 0 and 8 is the amount of water in the pipe at a minimum. Justify your answer. Okay? So, minimums, maximums could show up on the AP test. We've talked about this over quite a few different FRQ videos. How do we find maximums and minimums again? Okay, well, it comes out of 3.1. We take the derivative, we set it equal to 0. And then we plug that value, or those candidates, along with your two endpoints, into your original function, whatever your original function happens to be, okay? So we are talking about in the pipe. Okay, so first of all, derivative of in the pipe would be what? We talked about this in part B as well, but derivative of in the pipe is R of t minus d of t. And we set that equal to 0. Obviously this year again wouldn't necessarily be a calculator one, so you'd be looking maybe to factor that, combine like terms, do other solving strategies. This year, 2015, this one was a calculator one, so then they plugged this into their y equals R of t minus their d of t function, plug that into their calculator, calc to zeros, just like I demonstrated on the last problem, and you would get 1 0, well, 2 zeros technically, at 0 and one other value. But I'm going to say you would get 1 0 at 3.271658. The reason I call it just 1 0 is because remember you take the zeros and your endpoints. Well, 0 is already an endpoint, so it's already going to get tested anyway. But you take your zeros and your endpoints and you plug them into your original function. And again, we're talking in the pipe, so that's our original function. Okay? So amount at t equals 0 would be 30 plus the integral from 0 to 0 of r of t dt minus the integral from 0 to 0 of d of t dt, which is 30. Amount at t equals 3.271658 is 30 plus the integral from 0 to 3.271658 of r of t dt minus the integral from 0 to 3.271658 of d of t dt. Plug that into your calculator and you should get 27.964, and then amount at t equals 8, 30 plus the integral from 0 to 8 of r of t dt minus the integral from 0 to 8 of d of t dt, which is 48.543. And so at what point are we at a minimum? Okay, well our minimum is, if they ask me for the minimum value, it would be 27.964. But they're asking at what time t are we at a minimum? And so that would be at t equals 3.271658. Okay. This was worth 3 points. Whoops. 3 points. One was for setting your derivative equal to 0. I've talked about several times over different videos that when I read maximums and minimums, absolute maximums and minimums, I don't like solving the whole problem initially. I usually move on and kind of solve the other parts of the problem that I can, and then I come back and I do the maximum and minimum at the end.